Today, we're going to pull back the curtain on one of modern medicine's greatest, well, magic tricks, the X-ray. It really seems like something straight out of science fiction, right? A machine that can literally peer inside your body. But it's not magic. It's just pure, awesome physics. So let's break down exactly how it works.
I mean, we've all been there, lying on the table, and you can't help but wonder, how is this thing seeing my bones? Well, it's because X-rays are just a form of super high-energy light. They pass right through your soft tissues, but they get stopped in their tracks by dense stuff, like bone. And the secret to making that special kind of light? Well, it all starts inside a very unique device.
Yep, the whole show, from start to finish, takes place right inside this highly specialized piece of gear. You can think of it as a miniature particle accelerator, a high-energy collision chamber, and a ray gun all rolled into one. And the hero of our story today? It's a single, tiny particle, the electron. We are going to follow that one little electron on its entire wild journey through 5 key stages, from the moment it's born to its crazy high-speed flight, its dramatic final collision, and then how the aftermath of that crash becomes the X-ray image that we all recognize. Okay, first things first, to tell this story, we need some electrons, and to get them, we have to go to a very, very hot place. So, inside the cathode, that's the negative side of the tube, there's this tiny little filament. It's made of tungsten. Now, tungsten is the absolute perfect material for this job. For one, it's great at letting go of its electrons, and two, it has an insane melting point, over 3,400 degrees Celsius. It has to be able to withstand some seriously extreme heat for what comes next. See, we run a current through that tungsten filament, and we heat it up until it is literally white hot. This process has a fancy name, thermionic emission, but you can just think of it as boiling electrons off the surface of the metal. It creates this little cloud of free-floating electrons, just like steam rising from a kettle. But we can't just have this electron cloud spreading out all over the place, right? That's no good. So it's surrounded by something called a focusing cup, which is also negatively charged. And, since like charges repel, this cup acts like a lens. It kind of corrals all those free electrons into a tight, focus beam and points them exactly where we need them to go. All right, so our electron has been born, it's been aimed, now it's time for stage 2 of its journey, a massive, high-speed leap right across the X-ray tube. So how do we get it to move so fast with a huge voltage potential? We're talking somewhere between 50,000 and 150,000 volts between the negative cathode and the positive target, which is called the anode. This creates this incredibly powerful electrical field that just grabs hold of those electrons and yanks them across the gap at almost the speed of light. It's an incredible acceleration. Now, the entire X-ray tube is a glass envelope that's had pretty much all the air pumped out, creating a near-perfect vacuum. Why do that? Well, because we need the electron's path to be completely clear. We don't want it bumping into any pesky air molecules along the way. Nope. We want one single massive collision at the very end of its journey. Okay, so after being generated and accelerated, our electron is about to have the most important and, well, the final moment of its life, the impact. This right here is where the magic really happens. But before we see how the X-ray is actually made, we have to talk about the process's biggest byproduct. And honestly, its greatest challenge. All of that incredible kinetic energy from those speeding electrons, it has to go somewhere when they crash. And here is the staggering reality of it all. When those electrons slam into the anode target, 99% of their energy is converted directly into heat. A massive, massive amount of it. Only a tiny 1% sliver of all that energy actually becomes the X-rays we want. The whole process is unbelievably inefficient. So what's going on in that tiny 1%? How does an electron's kinetic energy magically transform into an X-ray photon? Well, it turns out it happens in 2 completely different ways. So the most common method, which accounts for about 80% of all the X-rays, is called Bremsstrahlung. That's a German word that basically means breaking radiation. So imagine our electron as a bowling ball just hurtling towards the heavy nucleus of a tungsten atom. It doesn't hit it dead on. Instead, the nucleus's powerful positive charge makes the electron swerve and slow down. It literally hits the brakes. And all that lost energy from braking, it gets released as an X-ray photon. Now, the second method is called characteristic radiation. And you can think of this one like a game of cosmic billiards.
Our incoming electron, the cue ball, smashes directly into an electron in one of the target atom's inner shells and just knocks it completely out of orbit. Bam! This leaves an empty spot, a vacancy, and an electron from a higher energy outer shell immediately drops down to fill that gap. As it falls into that lower energy state, it releases a very specific, predictable amount of energy as, you guessed it, an X-ray photon. So let's just quickly put them side by side. Bremsstrahlung happens when the electron interacts with the nucleus, and that makes a whole range of different X-ray energies. Characteristic radiation, on the other hand, comes from an interaction with the shell electrons, and it produces X-rays of very specific, predictable energies that are, well, characteristic to the target material, in this case, tungsten.
We've done it. We've created X-rays, but right now they're just flying out in all directions with a whole mix of different energies. So the final step of the journey is to take this chaotic burst and refine it into a precise, useful tool for medical imaging.
Now, here's a cool little insider detail for you. The X-ray beam isn't perfectly uniform. Because that anode target is set at an angle, the X-rays created on the heel side of that angle actually have to travel through more of the target material just to escape, which weakens them. This is called the anode heel effect, and smart radiographers actually use this to their advantage, placing the more intense side of the beam over the thicker part of a patient's body. Pretty clever, right?
So there's always this key trade-off when you're designing the anode. A smaller angle gives you a smaller focal spot, which means a sharper, more detailed image. But it also makes that heel effect much more pronounced, giving you a less uniform beam. So it's this constant balancing act between image detail and beam uniformity. Now, radiographers basically have two main dials to control the final image. The first is tube current, or MA. This controls the quantity of X-rays. You turn up the current, the filament gets hotter, you boil off more electrons, and you get more X-ray photons. Simple. The second dial is tube potential, or kV. This controls the quality, the penetrating power of those X-rays. Higher voltage means the electrons hit the target harder, creating higher energy, more powerful X-rays that can get through denser tissue. And for the final touch, right before the beam leaves the tube for good, it passes through some filters. These are just thin sheets of metal, like aluminum or copper, and their whole job is to absorb the low-energy or soft X-rays. See, these photons aren't powerful enough to actually make it through the patient to create the image, so they would just add to the radiation dose without any benefit. This filtration is a super important safety feature.
So there you have it, the entire wild ride. An electron is generated from a super hot filament, accelerated across a vacuum by an immense voltage, smashes into a tungsten target, converts just 1% of its energy into X-rays through two different processes, and then that resulting beam is carefully shaped and filtered into a precise diagnostic tool.
You know, what's truly mind-boggling to me is that this entire violent, high-energy process, it all happens in the blink of an eye every single time someone gets an X-ray. It really makes you wonder, what other incredible, invisible physics is shaping the world all